And the topic of my talk, it was already introduced as well, but I'm going to insist on that. Influence of the mandatory disconnection of distributed generators on the voltage stability of the bulk power system. So, well, I guess it fits well the sequence of Dr. Nelson's talk, because as you can see, it's such an ambitious and challenging research. So close, quite as important as what Dr. Nelson told us about. But nevertheless, I hope you like the presentation. And it already starts with, okay. I'm going to, well, this is a brief presentation outline. I'm going to introduce the problem, give you an overview of it, talk about the proposed approach for modeling the problem. And this is probably the most important aspect of the talk, because you will see that this is intended as a proof of concept study. And so the approach for modeling and showcasing the problem is perhaps more important than the solution we propose. Then I'll present the test system and its features, the simulations that we made and the results that we got, and the proposed solution that is still at a very early stage. So it's quite a simple solution. We have to do much more research on that, an evaluation of the results. And after that, if time permits, I'm going to talk about a proposed approach for handling the real-time problem, because this talk will be about short-term voltage stability, which means we have to solve differential algebraic equations, so it cannot be done in real time. And finally, the conclusions of the talk. So to give you the problem overview, well, distributed generator, the closest I can get to Dr. Nelson's talk is to talk about distributed generation. Small generators injecting power into low and medium voltage grids, which are a feature of our time, an engineering solution for an old problem that was that centralized generation of power has become, from the environmental point of view and also from the economical point of view in certain aspects. So distributed generation is already a reality, but there are still some drawbacks to its usage, and to avoid these drawbacks, some requirements, some rules have to be put in place to avoid that these generators harm or damage or worsen the functioning of the system. So one of these rules is that there must be undervoltage protection at each point of common coupling of distributed generators. Well, this makes sense. If the voltage drops too much, the generator must disconnect. This is kind of usual. But what I will try to show you is that sometimes, under certain conditions, these disconnections, when they happen as a cascading event, a cascading failure, they can worsen voltage stability problems in the bulk power grid, not only for the distribution systems, but also for the bulk power grid. For example, if a fault in the transmission network happens, it may produce a sag in the magnitude of the voltage to an extent that would trip a DG unit and this can have this can trigger a cascading event. So this is, I'll show you an example of that later. Well, currently, the generators connected to distribution feeders are not modeled in stability studies, at least by the ONS, which is the Brazilian TSO, but several other TSOs around the world also do that, also take this, use this as common practice. However, detailed modeling of this, well, obviously there must be a reason why these generators are not modeled. Detailed modeling of these generators is infeasible because, especially for stability studies that involve the solution of differential algebraic equations, you have such a large computational burden that if you enhance the model, you may render the simulation infeasible. And that's what usually happens. So we have to come up with simplifications. And the simplification that is typically used is this one. To basically consider the distributed generators as negative loads. Discount them from the gross load demand of the feeder and or model the bulk power system as seeing a net the net load, which is the total load minus the generation that is connected to this feeder. However, is it advisable to do that? Is it advisable to simply ignore the presence of these generators and consider them as negative loads? Well, let's talk about the bigger picture first. To give you an overview of distributed generation in Brazil, if you look at the amount of decentralized dispatched generation in Brazil in 2015, it was up to 13.5% of the total load. And if you break this into the biggest sources, you will find that 4% come from wind, and in terms of distributed generation, around 5% come from small hydro, and around 5% as well come from thermal based on biomass. So if you sum up and approximate, you can say that a little less than 10% of the total load of the Brazilian interconnected power system was this total load was supplied by distributed synchronous generation in 2015. And when I say distributed synchronous generation, and the reason I highlighted small hydro and thermal was the fact that these are synchronous generators and they are directly connected to the grid. So they do not require inverter-based or power electronics interfaces to connect to the grid, which make them much less expensive. So this is a very good alternative to supply power. And this is why we see such a high growth in this kind of generation. So to consider them as simply negative loads, so you're in such a way you are considering 10% of the load as you're not adequately modeling as much as 10% of the load, or a little less than that. So what is the idea for this study? This is intended as a proof of concept. So we did, the first thing we did is the study was not carried out in Brazilian system, in part of a Brazilian system, because we wanted to make it, first, reproducible, and second, we did not want to associate this to a particular portion of the Brazilian system or whatsoever. So we chose a benchmark system for short-term voltage stability studies that was developed by the IEEE. It was a task force of the IEEE. And if you are interested, you can retrieve the full data for this benchmark system at this address. So if you're interested in that, you can have the slides and then retrieve the full data for this system from this web address. Well, the main proposal, to establish a trade-off between accuracy and complexity to account for undervoltage disconnection of DG units. So what was our trade-off? I mean, there can be many others, but we chose this one. We came up with a simplified algebraic model for DG. We could not afford to model DG as differential by differential equations. It would come back to the infeasibility of solving the equations. So we came up with an algebraic model, but a simplified one, dividing the DG into 3 groups according to their electric distance from the substation. So you have group 1 that is connected to the vicinity of the substation, group 2 connected to the middle of the feeder, and group 3 connected to the end of the feeder. So this is basically lumping distributed generations or generators into these 3 groups. But what's the effect of that? Well, the first thing we did was we had a base case for the power system. So here we have the bulk power system, the substation bus bar, and we have the base case load. This is what the bulk power system sees. We did not want to change the operating point of the bulk power system. So what we did was we inserted an extra load. You're going to see that in all the examples, this extra load was 10% of the total load of the base case. And so we inserted this total load. This would change the operating point seen by the bulk power system. But to avoid that, we inserted the 3 DG groups. Actually, this figure, I just realized that this figure should be better better presented because group 2 is not directly connected to the bus. But anyway, I hope you remember the definition. So we have these 3 groups, and the sum of the power produced by these 3 groups matches the total DG supply plus losses. So from the bulk power system viewpoint, it only sees the base case load as is the common practice for the TSOs around the world. Well, after that, we had to come up with an approach to model the voltage drop for each of these groups. So how can we, as the total load of the system increases, how does the voltage at each of these three groups decreases so we can actually measure their impact on the dynamics of the system? Well, we made several simulations using a generic feeder and came up with statistic distributions for the voltage drops at the points where each of those DG groups were connected. So for group 1, the average voltage drop was 0%. Well, this obviously makes sense because it is connected directly at the substation bus. And this average voltage drop is measured as a percentage of the voltage at the substation bus. For group 2, those generators that are connected to the middle of the feeder, we found out that the average voltage drop is around 3.5%, and for group 3, around 4.6%. And the standard deviations are small, so we thought it was a good idea to consider these average voltage drops as fixed settings in the algebraic DG model. So whenever the voltage at the substation bus drops, what happens is that the voltage at the DG groups 1, 2, and 3 drop proportionally according to these percentages. The other thing that we had to analyze is how undervoltage protection for these distributed generators are adjusted. So we made broad research taking into account several different grid codes of several different utilities in Brazil. And we found out, this seems like a magical number, but I'm sorry, it's just how it came out. We found out that we could group these adjustments into three different groups. So they were grouped by similarity, and this resulted in 3 different cases. So when I say case here, I mean the type of adjust of undervoltage protection. And here you see case 1, well, for each of the cases we have a pickup value and a delay time for the relay to send the tripping signal to the DG unit. So you can see that case 1 is the most stringent requirement. So the pickup is 0.92 per unit for group 1, 0.95 per unit for group 2, and 0.95 per unit for group 3. And from case 1 to case 3, it goes in descending order of stringency, or they become less stringent as the number of the case increases. Well, the test system, as I mentioned before, is usually known as the Nordic test system. It was developed by an IEEE task force, although it was around for several cases, but it was this IEEE task force made it a benchmark for short-term voltage stability studies. And for this reason, we used this test system to make the study as general as possible. It's composed by 74 buses and 20 generators in the bulk power grid. And we're going to put focus in the next slides on these 20 generators, we're going to simulate the loss of each of these generators and see what happens. Well, one thing that is known about the system is that voltage stability problems usually arise when the load in the central area increases. So this is one key information that led us to do the following thing. The first is that the test system was set up in a base case where it operates with 7% of voltage stability margin as required by the ONS grid code. The feeder model with 3 DG groups was adopted for the load buses of the central area because this is the problematic area. So we wanted to we wanted to see what happened when the load increased in this area with the presence of DG. We have case 0 also, which corresponds to the base case of the benchmark system. In other words, the system with no distributed generation. All the load buses do not have any type of generation at all. So this is the unmodified benchmark test system. And for cases 1, 2, and 3, the total load in the central area was increased by 10%, and this increase was fully supplied by DG, as I mentioned previously. Last, the perturbation that initiates the transients is the loss of a generator in the bulk power grid. So let's see what happens if we lose by the N-1 criterion. Let's see what happens if we lose any generator in the power system, each of the generators in the power system, the bulk power grid. So how can I read this, this figure? Oh, this is case 0. And what we see is that if the system has no distributed generators, of course, there is no disconnection of DG. But also, this is an important thing, we preserved the stability of the system under the N-1 criterion by preserving the base case operating point. So you can see there are no unstable cases in this line. This is summarized in the next slide. Unstable cases are found when the proposed model for the distribution feeders is used. And then we have to go back to the cases. For case 1, which, as I mentioned, was the most stringent, what we see is instability for the loss of G14, 15, 18, and 20, and cases that are stable but result in the disconnection of more than half of the distributed generators in the system. So most of the cases result in this disconnection of more than half. Cases 2 and 3 are not so problematic, but still, if we look at G15 and G18, if we lose one of those two generators, we have short-term voltage instability. So to summarize that, the most critical cases are the disconnection of either G15 or G18. And in the following graphs, I'll show you the response of the system when G15 trips. And I'm going to illustrate the problem with the voltage at bus 1 and the sum of the active power delivered by the distributed generators. As this sum of active power decreases, you will see the cascading disconnection of these generators, cascading failure that will result in the instability problem. So here it is. Sum of DG active power. After generator 15 trips here around in about 1 second, there is an oscillatory transient, and after that you start to see the sum of the active power from DG to drop dramatically. And in some cases, there are some of the generators that are left in the system. So these cases are stable cases, but these are still stable cases, but there's very little power coming from DG left. And for the other situations, all the distributed generators are disconnected. Okay. So what we have is a successive disconnection of the DG units that results in voltage drop. So this is the result of that cascading failure, a sharp voltage drop compared to case 0, which is the one with no DG. So what you see is short-term voltage instability. So what is the problem? To summarize that, what is the problem? We lost a generator in the bulk power grid. This made it more difficult for the bulk power grid to supply the total load. But as we lost a generator in the bulk power grid, the voltage drop made the distributed generators start to disconnect due to their undervoltage protection. And then it worsens the problem because the load seen by the bulk power grid is also increased together with the loss of a generator. So this is the mechanism of short-term voltage instability. So as I told you, the proposed solution is at a very early stage. We just propose to use uniform adjust for the undervoltage protection functions with smaller voltage pickup values. Again, I don't know why we like 3 so much, but we studied 3 cases, 3 uniform cases, and what varies in these cases is the pickup value. So 0.85, 0.8, and 0.75 per unit. So here is what we have for cases 4, 5, and 6. So case 4, among the new cases that are shown, is the most stringent. And if in case 4, I still see instability arising when G15 trips. But for cases 5 and 6, there is no instability problem and no disconnection of DG. So this is one possible solution to the problem. So these smaller pickup voltages resulted in less disconnection of DG as expected. It happened for pickup values equal or smaller than 0.8 per unit, but of course this is not a value that could be generalized. It should be fine-tuned to a particular system. And just quickly, I'll show you, if you look at cases 5 and 6, they are superimposed here, so you can see that for undervoltage pickup values equal to or smaller than 0.8 per unit, disconnections were prevented, which resulted in stable transients. So you can see this curve. It's even better in terms of the resulting steady-state voltage value that in the base case of the benchmark power system. So in conclusion, The mandatory disconnection of DD units may cause unintended trip of these units. And what I just shown you is that they can worsen voltage stability problems in the transmission system. So they must be modeled to avoid a cascading failure. And once modeled, we are able to come up with adequate undervoltage settings at the point of common coupling to prevent this unintended disconnection. And so they're allowed, if they not contribute to the system, they do not, if they not contribute to the stability, they do not worsen the problem, at least. Of course, further research is still required to assess the impact of this less stringent voltage settings on the behavior of system equipment. It was not tested yet. It was just simulation-based. But this is a further direction of the research. But another research that is already under development is an approach to handle the problem in real time. Because remember, I was showing you the results of time domain simulations, which are very time consuming. So they cannot be applied in real time. What we did, another line of this research, was to develop an approach to handle the problem in real time by, and this is work that was already submitted to a major journal and awaits publication. I was hoping to have time to talk a little bit more about that, but unfortunately, I think my time's up. So I thank you again for your attention, and I'm open for any questions you may have. Thank you. Just last comment, if I may. The study was carried out as part of the PhD thesis of my student, Jonathan Andrade dos Santos, just to acknowledge his great work.
Thank you, Dr. Rodrigo. Then we switch to question, comment to audience. Please, Professor Kleber from Brazilian University.
So thank you for your quite interesting talk, Professor Rodrigo. Actually, I have some questions, but I need to summarize in maybe 2 questions. The first one, in your opinion, from which level of the G penetration level we need to be worried about it in this case?
Well, it's very hard to tell because it may be related to the topology of the system. It may be related to several types of factors. So you cannot come up with a very precise number for that, because different system topologies may present this problem, while others may not. What I have shown here is that for a level as low, in a sense, as 10%, the problem already arises. So what I can tell you is that for the study that we have made, 10% is already a penetration level to start so the red light is still on if we have 10%.
Okay, thank you. And another question is related to the other kind of protection functions used in anti-island protection. Do you intend to research the performance of this other protection functions in this kind of study?
Yes, we have been doing this already, but we are trying. Our first approach is try to understand how it works from the feeder perspective. So understand how it works on the distribution level is very important for you to make approximations that will still be valid for the transmission level. So we're starting to build a broader understanding of how the distribution level works from the substation bus onwards. And after we are confident on that, we will start making approximations.
Any other question? I have one. Please, you have priority.
If I may, because this is not really my area of expertise, but you've shown a slide where all your generators drop, and then in another case where was it 2 generators left over. Do you have an explanation for that? Because I cannot understand how these 2 remaining generators could keep up the network up and running. And the other question is there a difference on when you make this undervoltage switch off on the level of undervoltage on where you set the trip point on the result of your simulations?
Well, regarding the first question, what I have shown you is that there are cases in which you have there were 4 cases in that table. The stable cases, there's no disconnection of DG. The unstable cases, the cases where DG was lost by more than half, and the cases where DG was lost by less than half. So those cases may have fallen into this category that the DG was lost by less than half, and it is still a stable case that is shown there, but with only 2 or 3 DG connected. So I am assuming that they were, but to be fully honest with you, I would have to consult with my student to make sure that I'm giving you the correct answer. And can you repeat your second question, please?
The voltage level at the trigger point has any difference when you trip the generators. If you trip it at minus so many percent of the voltage level.
Well, this is the reason we made we came up with those percentages was we tried to be as accurate as possible, so we came up with statistical distribution that gave us an average. So those were average voltage drops that would occur at that point in the feeder. So if you change that, this obviously will impact the dynamic. You, when
you make the decision to trip the DG at a certain voltage level.
Okay.
Yeah. You make a decision to trip the DG when the voltage is below a certain threshold, and I'm asking whether where exactly setting this threshold, whether that would make a difference to your simulations.
I'm still not sure I understand, because the settings are I have summarized the settings in a previous slide. I'm sorry. There was each of those cases had a pickup value and a delay time. So those cases are the pickup voltages that are fixed for the tripping of the DG. What I've shown you is that if you make less stringent pickup voltage values, then you may not have the problem. But I'm not sure if that's an answer to your question.
Yeah, okay, thank you.
Unfortunately, I have no time to continue the discussion, then we stop here. And again, we thank Dr. Rodrigo Ramos by the presentation, and we thank it also to accept the invitation to contribute to your experience with us. Thank you, the audience. And now we have a break for the coffee break, and we return 3:40.